Welcome to Curiosity Repo, your home for cosmic queries and mind-bending science. Today, we're journeying to the far future to explore one of the most ambitious engineering projects ever conceived. What happens when a civilization's energy needs become so vast that an entire planet's resources are no longer enough? They might turn to the ultimate power source, their own star. This is the concept behind the Dyson sphere, a hypothetical megastructure that would enclose a star to capture nearly all of its energy output. First proposed by physicist Freeman Dyson in 1960, it represents the hallmark of a Type II civilization on the Kardashev scale. A Type II civilization has mastered the ability to harness the total energy of its parent star. For perspective, humanity is currently a Type 0.7 civilization, still struggling to efficiently use the energy resources of our own planet. The leap to a Type II status is monumental, requiring a level of technology and cooperation that is currently the stuff of science fiction. But how would a civilization even begin to build such a colossal structure? The most common image of a Dyson sphere is a solid, rigid shell completely encasing a star. While visually stunning, this idea is fraught with gravitational instability and engineering impossibilities. Any slight push or gravitational tug from a passing celestial body could send the shell crashing into its star. Furthermore, the tensile strength required to prevent such a massive sphere from tearing itself apart is far beyond any known material. A much more practical and stable approach is the Dyson swarm. Instead of a single, solid shell, a Dyson swarm would consist of a massive collection of independent, orbiting solar collectors. Imagine countless satellites, each harvesting solar energy and beaming it to a central collection point or directly to a home planet. These satellites would fly in a tight, coordinated formation, creating a dense cloud that effectively surrounds the star. This modular design is far more achievable. It can be built incrementally, with each new satellite adding to the civilization's total energy budget. There is no single point of failure, as the loss of one or even thousands of collectors wouldn't compromise the entire system. So, let's say a future civilization decides to build one. What's the first step? The most critical ingredient is, of course, raw material. An astronomical amount of it. To construct a swarm dense enough to capture a significant portion of a star's light, you would need the mass of an entire planet, or several. Freeman Dyson himself suggested a prime candidate for this cosmic deconstruction, Mercury. Mercury is the closest planet to our Sun and is rich in the metals and silicates needed for construction. Its low gravity and lack of atmosphere make it relatively easy to launch materials into space. A fleet of automated mining robots would descend upon Mercury, systematically disassembling it piece by piece. This material would then be processed and launched into solar orbit using electromagnetic catapults, or mass drivers. These mass drivers would fling trillions of tons of refined material into precise orbits, where self-replicating construction drones would get to work. These drones would assemble the raw materials into vast solar collectors, power transmitters, and habitats for the engineers overseeing the project. Each collector in the swarm might be a gigantic mirror, focusing sunlight onto a central heat engine, or a vast photovoltaic panel converting light directly into electricity. The engineering would be on a scale that dwarfs anything humanity has ever attempted. The swarm wouldn't be a simple, static cloud. It would be a dynamic, living system. Each satellite would need its own propulsion to maintain its precise orbit, avoiding collisions and adjusting to the star's gravitational pull. A sophisticated central AI would likely be required to manage the trillions of independent components, coordinating their movements, monitoring their energy output, and conducting repairs. The logistical complexity would be staggering. Once the energy is captured, it needs to be delivered. The swarm could use high-powered lasers or microwave beams to transmit the energy across vast distances to planets, space colonies, or interstellar ships. This network of energy beams would create a new kind of cosmic infrastructure, powering a civilization that has expanded throughout its solar system. With such abundant energy, projects like terraforming planets or launching starships at near-light speed become feasible. The Dyson swarm itself would become a new ecosystem. The structures could host habitats, allowing for a population far greater than any single planet could support. It would be a true city built around a star. So, if such megastructures exist, could we find them? Astronomers are actively searching for signs of these alien engineering projects. Building a Dyson swarm would leave a noticeable cosmic signature. A star encased in a swarm would dim significantly in the visible light spectrum. However, the energy captured by the swarm must be radiated away as waste heat, or the collectors would melt. This means a star with a Dyson swarm would glow brightly in the infrared part of the spectrum. Astronomers are using telescopes like the Wide Field Infrared Survey Explorer, WISE, to scan the skies for objects that are unusually bright in infrared but dim in visible light. This search for technological waste heat is a key strategy in the search for extraterrestrial intelligence, SETI. Finding such an anomaly would be powerful, albeit indirect, evidence of an advanced alien civilization at work. So far, several candidates have been identified and subsequently explained by natural phenomena, like clouds of cosmic dust. The most famous was KIC 846-2852, also known as Tabby star, which showed erratic and significant dimming, but further study has pointed towards natural causes. The search continues, because the discovery of a Dyson swarm would change everything. It would prove that we are not alone in the universe and that it's possible for a civilization to achieve a level of technological mastery that, for now, we can only dream of. It represents an optimistic vision of the future, one where a species has overcome its planetary limitations to reach for the stars in the most literal way possible. It's a testament to the power of ingenuity and the endless quest for energy and knowledge. Thank you for joining us on this incredible journey. If you enjoyed this exploration into the future of engineering, be sure to subscribe to Curiosity Repo for more deep dives into the wonders of our universe.